Hello everyone, welcome back to Physics 425. What I thought I would start with today is a temperature scale. So I've drawn one here. It's a log scale, so each division is a factor of 10, and this scale goes from 1000 Kelvin to 1 millikelvin, so that's 6 orders of magnitude. Now we haven't worked ours all the way down this scale, but I thought we would give an indication of where we are. So somewhere around here is 300 Kelvin, our room temperature. So here's room temperature at about 300 Kelvin. And if you had a cryocooler, say a single stage cryocooler, that's going to get you to something like 50 to 100 Kelvin, somewhere in that range. And so let's suppose you had a good single stage cryocooler and you get down to about 50 Kelvin. So a single stage cryocooler. And then, as we talked about, what you could do is you could run a second stage from the cold end of the first stage. And if you do that, you might get down to about 10 Kelvin. And so that's right around here, 10 Kelvin, and this is a two-stage cryocooler. The next thing we imagined doing was using a two-stage cryocooler to pre-cool some compressed helium-4 gas, and then doing a Joule-Thomson expansion to cool the gas further. And in that case, what you can do is you can actually liquefy the helium, and that happens at about 4 Kelvin or 4.2 Kelvin. So this is a Joule-Thomson expansion. What I want to talk about today is a way to take our bath of liquid helium and reduce the boiling temperature of the liquid, and that will let us get down to the range of about 1 Kelvin. Okay, so before we get into that, let me just make a couple of points. So first, we discussed the Stirling cycle in detail. However, there are other cryocooler cycles in use, and in fact, maybe they're even more common. One type is the Gifford-McMahon cycle, or it's the GM cryocooler. And so you can find lots of commercial products here. The idea is the same. You're going to try and isothermally expand a gas at the cold stage to remove heat Q1 from the cold reservoir at temperature T1. It's just how you get the gas into that isothermal expansion, and how you complete the rest of the cycle varies a little bit in the details. Relatively new, like in the last few decades, are pulse tube cryocoolers. And these are now actually taking over because they have some advantages. They have no moving parts, so there's no piston that's used to push the gas up and down. And that means that if you build an experiment on the end of a pulse tube cryocooler, it's going to be more immune to, or there's going to be less vibrations than you would have with a Stirling or Gifford-McMahon cryocooler. And also because there's fewer moving parts, that means they're more reliable, they don't break down as much, they require less maintenance. And finally, a two-stage pulse tube cryocooler can reach temperatures as low as 2 Kelvin, so quite cold. Okay, so the goal for today is to see how we can use pressure to manipulate the boiling temperature of a bath of liquid helium. We're going to talk about liquid helium because this is a low temperature class, and that's typically the liquid that we're going to work with, but this applies more generally to other systems as well. Okay, so actually, while we're at it, why don't we just list some boiling temperatures of other cryogenic liquids. And this is going to be at 1 atmosphere of pressure above the surface of the liquid. So oxygen has a boiling temperature of 90 Kelvin. Argon is close to that at 87 Kelvin for liquid argon. Nitrogen is a common one because nitrogen is abundant and inexpensive, and so it boils at 77 Kelvin. And so you may have seen demonstrations using liquid nitrogen, or you may have handled some yourself. One fun thing is that if you're using liquid nitrogen, sometimes you see a little pool of liquid on some object that's been cooled to 77 Kelvin. And if that, assuming that that's not liquid nitrogen, it could be a little puddle of liquid oxygen because it's cold enough to condense the oxygen from the air. Liquid oxygen's fun because it's paramagnetic, so you can drag it around with a magnet. Neon has a boiling temperature of 27.2 Kelvin. Hydrogen is 20.3 Kelvin. You'd have to be a little bit careful with liquid hydrogen because the vapor, if you have hydrogen gas and some oxygen around, that could ignite. Liquid helium is 4.21 Kelvin, and so this is obviously another important one for us. And we will actually also talk about the isotope of helium, helium-3, which has a slightly lower boiling temperature. Okay. So before we get into this, I think intuitively you already know this effect. So if you were planning to go on some kind of trek, and so you're an overnight trek, you're going to hike up a mountain, and then you're going to spend the night up there. And so you get to your camp, and you're going to make yourself a pasta dinner. You boil a pot of water. You stick your dried noodles in there, and you find that you have to boil them for a longer time to get them to the right firmness or softness. And the reason you have to cook them longer is because at a higher elevation, where the pressure of the atmosphere is less, the water boils at a lower temperature. And so we're going to use the same effect for our little bath of liquid helium. We're going to reduce the pressure above that bath to lower its boiling temperature. The opposite also works, right? If you have a pressure cooker, what does a pressure cooker do? You put some meat that generally takes a long time to cook in there, and you add some liquid into your pressure cooker, and then you close it up, and it's completely sealed. And as you heat the liquid inside, the vapor, some of the liquid turns into a vapor, but now you have a closed space, and so as you add more and more vapor into this closed fixed volume, the pressure goes up, and as you increase this pressure above the liquid, its boiling temperature goes up. And so you can increase the boiling temperature of, say your liquid's primarily water-based from 100 Celsius up to about 120 Celsius. And because you're cooking at a higher temperature, your food cooks quicker. Okay, so before we get into all of this, I want to start by trying to come up with an interpretation of enthalpy. We've used this concept of enthalpy a few times already, and we're going to use it again. Let me just remind you what it is. It's the internal energy U plus PV. So before we do the enthalpy, let's start with just a change in internal energy and see if we can interpret that quantity. So du is dq minus pdv, so heat added, and then pdv is the work by the gas. So for an isochoric process, so a process at constant volume, the increase in internal energy, right? If we have a constant volume process, then we're going to say dV is equal to 0, and just the change in internal energy, du, is just equal to dq, the heat added to the system. So if we add a heat dq, then the internal energy goes up by the same amount. The increase in internal energy is equal to the heat added. Okay, so that's internal energy. What about enthalpy? So first let's just, H is equal to U plus PV. And so then we take a differential. du is dq minus pdv, and then pv, so it's going to be plus pdv plus vdp. And so dh is equal to dq plus vdp. So let's do what we did above. We got rid of the minus pdv by saying, well, let's think about a process that's constant volume. Well, we can also get rid of vdp in this case by saying, well, let's think about a process that's at constant pressure. So for an isobaric process, isobaric means constant pressure, dP is 0. The increase in enthalpy of a system is equal to the heat added. Okay, so change in internal energy is the heat added when the volume stays constant. Change in enthalpy is the heat added when the pressure stays constant. There are, of course, examples of processes at constant pressure. So this could be any process in an open beaker. So what could you do in an open beaker? You could boil a liquid, and if the beaker's open, then the pressure above the surface of the liquid is always 1 atmosphere. You could mix chemicals together, and then you could observe a chemical reaction. Again, if it's in an open beaker, the reaction occurs at a constant pressure. And so anything where you have P equals to, say, a constant above something happening inside a beaker. Okay, we can go a little bit further with our trying to develop our understanding of enthalpy. And so we're going to come up with a relationship between latent heat and enthalpy. What latent heat is, it's the amount of heat that you need to add to something to cause a change of state. And so, for example, let's consider a liquid of volume V1 at its boiling temperature. So now we're going to take a quantity of heat and we're going to add it to our system. We're going to call that quantity of heat L. It's going to be the latent heat. And so this is added, and this amount of heat is sufficient to completely vaporize the liquid. So we transform the liquid completely into a gas. After this vaporization, the volume of the gas is V2. And so we could just keep in mind that if we had some volume of liquid and so the pressure above the liquid is 1 atmosphere, and then we turn it into a gas, and the pressure of the gas is 1 atmosphere, that gas occupies a huge volume compared to the liquid. So in this particular example, V2 would be much bigger than V1, and I think we'll actually make use of that fact a little later. So if the vapor is expanded against a constant pressure, then so change in internal energy is dq minus p dv. And so we know that, okay, let's take the internal energy. Change in internal energy is U2 minus U1. So U2 is the internal energy of the vapor. U1 is the internal energy of the liquid. dq is the heat added. We said that was going to be L. And then we said pressure is a constant, so pressure doesn't change. And then we just have the change in volume, which we said for the gas was V2 and for the liquid is V1. We could rearrange a little bit. Let's isolate L. And if we do that, what we get is U2 plus PV2 minus U1 plus PV1. And you might recognize U plus PV is just the enthalpy. So this is the enthalpy of the gas, and this is the enthalpy of the liquid. And this heat that we had to add to vaporize our liquid, which was the latent heat, is just equal to the change in enthalpy. And so L is equal to the change in enthalpy. So therefore, during a change of state at constant pressure, the latent heat of transformation is equal to the change in enthalpy. So we specifically thought of vaporizing a liquid, but there was nothing special about this being the liquid to gas transformation. It could be other changes of state as well. Okay, our goal for today, or one of our main goals, is to derive the so-called Clausius-Clapeyron equation. Clapeyron is probably the right way. And so what is this equation going to tell us? To understand what it's going to tell us, we need to start with a picture of a generic phase diagram. The phase diagram is going to be a plot of pressure versus temperature. And it's going to have a few different curves here. One curve over here. Let's have another curve somewhere over here. We'll change its color. And then we'll have a third curve that's going to do something, has a bit of a funnier shape, something like that. Okay, so what these lines on the phase diagram, pressure versus temperature, represent are coexistence curves. So in this phase diagram, at high pressure and low temperature, that's when objects are in their solid state. At low pressure and high temperature, that's when they're in their gas or vapor state. And then there's some intermediate region where they're liquid. And so these three lines that I've drawn, these lines separating two phases, are called coexistence curves. So the boundary between, say, a vapor and a liquid defines the boiling temperature. And when you're exactly on this line, that's when the two phases, liquid and vapor, can coexist. Then the red line between a liquid and a solid defines the freezing point. And again, when you're right on this line, that's a coexistence curve, so the two phases exist together. This point where all three meet is called the triple point, and that's where all three phases can coexist at once, and that happens only at a single point. Okay, so what is this result that we're going to try to derive, the Clausius-Clapeyron equation? So this equation is going to give us the slope of tangents to the coexistence curves. Okay, so, because we're gonna, in our application, be thinking of a boiling bath of liquid helium-4, I can pick a point on this phase diagram on the liquid-vapor coexistence curve, and the slope of this line is dp dt, and so we're going to calculate a result for dp dt. So we will show that dp dt is going to be given by this latent heat, which we just showed is equal to the change in enthalpy, divided by T, divided by the change in volume, where the change in volume is like the V2, the volume of the gas, minus V1, the volume of the liquid. Okay. So to get this result, we'll start with the entropy, and we get to choose which thermodynamic variables we'll express our entropy in terms of, and we're going to choose volume and temperature. So S is a function of volume and temperature, so that if we take a differential of this entropy, it's going to be the partial derivative of S with respect to V at constant temperature times dV, plus the partial of the entropy with respect to T at constant volume times dt. Okay, so if we're in a phase change, let's go back to this diagram, and let's imagine we are working at this point on the coexistence curve of the vapor and the liquid. And so if we're operating at this point and the pressure of our system is constant at, say, some whatever P naught, then we have to be on this curve, and if we're at pressure P naught, then the only possibility is we're at temperature T naught. And so there's a fixed pair of pressures and temperatures. So during a phase change, which is occurring at constant pressure, we must have T is equal to a constant. Okay, so if we operate our phase change at a constant pressure, then temperature is constant, and so dt is 0. And so then what we have is that the change in entropy is going to be ds dv at constant temperature dv. So this is a result that we'll come back to and use in just a minute. So we have a bit of an aside because we have to develop a Maxwell relation. You may remember Maxwell relations from thermodynamics or StatMech or something like that. So what we're going to do is we're going to start with the Helmholtz free energy. And if you don't remember what the Helmholtz free energy is, let me remind you. It was F was equal to U minus TS. The Helmholtz free energy is really useful in StatMech. It's used all the time. So let's take the differential of this Helmholtz free energy. dF is du, minus T ds minus S dt, but du is dq minus P dv. Then we have minus T ds minus S dt. But you remember that dq can also be expressed as T ds. Then we have minus P dv minus T ds minus S dt. And so TDS and minus TDS cancel, so that we have dF is equal to minus P dV minus S dt. Okay, so let's imagine that we had a constant temperature, for example, so that the dt vanishes. Then we could divide by dv, and we would have P is equal to minus df dv. So one expression is P is equal to minus df dv if temperature was constant. Okay, and then we could do the other thing. We could say, well, what if the volume was constant? If the volume was constant, dv would be 0, and we divide by dt, and we would get S is equal to minus df dt if volume is constant. Okay, then let's take the temperature derivative of the pressure, dp dt, and we'll do this at constant volume, is minus d by dt. Now P was df dv at constant temperature. We have already got the minus sign out there, and then we had to do this at constant volume. Okay, and then let's take a volume derivative of the entropy, ds dv, and we'll do that at constant temperature, is equal to minus, so d by dv, and entropy was df dt, so constant volume, constant temperature. Okay, good. So if you look at these two things, they're the same except for the order of derivatives, right? We have the Helmholtz free energy, and then we have a temperature derivative and a volume derivative. Here we have the Helmholtz free energy on the right, and then we have a volume derivative followed and a temperature derivative. But the order of derivatives doesn't matter. And so these two things are equal, and if those two are equal, it must be that dp dt at constant volume is equal to ds dv at constant temperature. And this is our Maxwell relation that we needed. It's useful because if we go back and look at number sign, or I think star, equation star, we had ds dv at constant temperature. And our Maxwell relation has ds dv at constant temperature. And so we can replace that with dp dt. That's useful because we have a phase diagram of pressure versus temperature. And we said we were going to try to find slopes of tangent lines, and that's dp dt. So you can start to see where we're making some progress. So, returning to equation star, we have ds is equal to, let's just write down, I guess, the original expression. And it looked like this. And so we're just going to use this Maxwell relation over here to say that ds must be equal to dp dt at constant volume times dv. Okay, good. So we now assume that we're boiling an open pot of liquid water or liquid helium or whatever. The pressure above the liquid surface remains constant. And so therefore, from the coexistence curve, on the phase diagram. The temperature is equal to a constant, and the slope of a tangent line dp dt is equal to a constant. Okay, and so we kind of made that point already, right? We said if we're working with this phase diagram and we're at a constant pressure and we're stuck on this coexistence curve, we could only be at one temperature. And if we're stuck at pressure and temperature, then when we draw a tangent line, there's only one tangent line that we can draw, and its slope, dp dt, is a constant. Okay, so our new version of equation star is up here. And so what we're saying then is that if we were to integrate ds, that's going to be the integral of dp dt dv, but dp dt is a constant, and so I can take it outside of the integral, and therefore the integral of ds is just delta s, the integral of dv is just delta v. We get that dp dt is equal to delta s divided by delta v. Okay, to go a little bit further, let's again return to enthalpy. H is U plus PV. We may have done this already, but I'm going to do it again. So dH is going to be, let's see, du plus P dV plus V dP. But du is dq minus P dV. There we go, plus P dV plus V dP. Cancel, cancel. But dq is T ds, and we go plus P dV. And then we say for a phase transition at constant pressure and temperature, we say that dP is going to vanish, and we have dH is equal to T ds, but T is a constant, so we can integrate, and when we integrate, we would say delta H is equal to T delta S. But we have a delta S over here, and so if we solve for delta S is equal to the change in enthalpy divided by T. But we showed that the change in enthalpy was just the latent heat, the heat of transformation. And so delta S is L over T. And we're going to take this delta S is equal to L over T, and we're going to bring it over here. And therefore, what we have, we finally have the desired Clausius-Clapeyron equation, which is dP dt was equal to delta S, which is L over T divided by delta V. Delta V is the V2 minus V1, the change in volume when you go through your phase transition. Okay, so like we've been talking about, what we're going to be interested in is the liquid to gas phase change. And so let's see if we can apply this result for, the slopes of a tangent line to the coexistence curve to this particular case. We already alluded to this, that delta V was going to be the final volume when we vaporized all of our liquid, so it's all of a gas, minus the liquid volume. And if this is all done at constant pressure, the gas occupies way more volume than the liquid, so this is approximately just equal to the volume of the gas. And in that case, our dp dt becomes approximately L over T times the volume of the gas. Okay. The next step is, let's treat the vapor above our liquid as an ideal gas. That should work reasonably well as long as we're not somehow working at very high pressures. So PV is nKT, so then we could write that the gas volume, where I'm going to drop the gas subscript now, is nKT over pressure. So that dp dt then, so we have a 1 over volume, so we'll have L times P divided by nKT, but then we have already another T in the denominator, so we get nkBT squared. Okay, we'd like to integrate this equation, and if we do that, we could have, if we rearrange it, let's divide by P, so we get dP over P, and then multiply by dt, that's going to be L over nkBT squared dt. Okay, then we can integrate both sides. In general, the latent heat L can be temperature dependent. In general, L can be temperature dependent. And if that was the case, you could only do the integral on the right-hand side if you knew how L was varying with temperature. It turns out, however, for liquid helium, the latent heat doesn't change much. Between 1 Kelvin and 4 Kelvin. Okay, I'm going to try and see if I can add a picture here. And so I think the latent heat that I want to add is this picture. And let's see if I can make this a bit bigger. Sorry, that didn't work. Oh. Here, let's see. I want to just expand this picture not expand the whole thing. Here, I'll try this one more time, and if I can't do it, I'll give up. Oh, I think I got it a little bit. Okay, good. Let's call that good enough. So this is a plot of the heat of vaporization of helium. So heat of vaporization is equivalent to the latent heat. This is a specific measurement, so it's per unit mass of the helium. So it's joules per gram. And from 4 Kelvin is here, to this only goes to 2 Kelvin. So from 4 Kelvin to 2 Kelvin, we can see that the latent heat is only changing from about maybe around 22 to 24. So it's changing by less than 10%. In fact, I think I've got another picture here, and so at the risk of using a lot of time again, I'm going to try to add it, and so I think it's this one. And let's move it to the next page. And so that's probably big enough as it is. And so these are the actual data of the latent heat as a function of temperature. So here's temperature and here's latent heat. And so it's going from 2 Kelvin, it's 22.8. It goes through a maximum at about, reaches 23.7 at 3 Kelvin, and it starts to drop again. It's only once you get above about 4 Kelvin that it starts to change rapidly. But if we're thinking of liquid helium, we've already got it at an atmosphere of pressure. We've already got it boiling at 4.2 Kelvin, and we're trying to go to low temperature below that. And so it's a reasonable approximation to treat L as a constant. And so we're going to say that this is approximately constant. And so now what we'll do is we'll integrate. And so we have the integral of dp over p is equal to, we're going to treat L as a constant, and then I think we have an nkb. Yeah. nkb, and then we have a dt, and I think it's over t squared. And so when we evaluate this, then we get the ln of the pressure is approximately equal to, we integrate 1 over t squared, we get minus 1 over t, so we get minus L over nkb, and then 1 over t, and we'll have some integration constant. So this is an integration constant. Okay. So if we exponentiate both sides, we can get that P is equal to B. Again, another constant. I guess it's just equal to e to the b prime times the exponential of minus L over n kbt. Or really what I care about is that P is proportional to the exponential of minus L over n kbt. And what's interesting about this is that if I was to plot this function, I'll show you what it, first let's just point out that this is the vapor pressure. So if you plot this function of the vapor pressure as a function of t, we're plotting the exponential of minus 1 over t. And what that looks like is something like this. It shouldn't curve down, but it kind of increases but slowly out here, and over here it decreases rapidly. So if we look over here at high pressures and high temperatures, if I was to take the vapor pressure above the liquid and reduce it by just a little bit. Okay, so we take a small delta P, then what we end up with is a large delta T. On the other hand, if we were already at low temperatures, then what we could do is we could try to change the vapor pressure by a lot. So we could take a large delta P, and if we did that, we would only get a relatively small delta T. And so this temperature here corresponds to the boiling temperature, and this corresponds to the vapor pressure. And so out here somewhere might be like close to an atmosphere or something. Sorry, I got that wrong. Over here might be somewhere around an atmosphere. And so if we're at an atmosphere and we're boiling our liquid at 4.2 Kelvin, if we use a pump to remove some of the vapor above the boiling liquid and thereby reduce the vapor pressure above the liquid, we'll see the boiling temperature of our liquid go down by quite a bit. A small change in pressure results in a big reduction in the temperature. However, if we're already at a low temperature, maybe around here is 1 Kelvin, then the vapor pressure is already low. So first of all, it's hard to get the pressure lower unless you're using a very big pump. And even if you are using a very big pump to get a reasonably large change in the pressure, it's only going to result in a very modest reduction in temperature. So this effect of manipulating the boiling temperature of the liquid works well when you're at high pressures, and then the effect becomes less and less and less as you go to lower pressures. So initially, when you're at high pressure, we can lower the boiling temperature of the liquid by using a pump to lower the vapor pressure. Eventually, the pressure gets low, and the temperature changes associated with further reductions in temperature, further reductions in pressure become small. So I just want to end here by trying to insert a couple more pictures here. This is a plot of the vapor pressure of liquid helium-4 as a function of temperature. And so this one's a little bit harder to read, but what we have is, let's look at the axis on the right-hand side. So this is pressure in atmospheres. So 1 atmosphere of pressure is up here. This is 1 atmosphere. And if we come down to our temperature axis, this is 4.2 Kelvin. So again, this is the same plot that I was trying to sketch above. This is the vapor pressure of helium-4, and this is the boiling temperature of the liquid. The reason it looks a little bit different than the picture that I drew is because I drew my plot with linear scales on both the pressure and temperature axis. This plot has the pressure on a log scale and the temperatures on a linear scale. Okay, and down here, when you get to 1 Kelvin, the pressure is at what? The pressure, here's 1/1000th of an atmosphere. This is 1/10,000th of an atmosphere. And so you have to get to a temperature, a boiling temperature of 1 Kelvin, you have to reduce the pressure by, a factor of 5,000 or something like that. And that turns out to be about the practical limit of what you can do using to cool your liquid helium bath by reducing the vapor pressure. So the practical limit is a boiling temperature of around 1 Kelvin. If you take it to the extreme, you get a very large pump and you connect it very close to your bath of liquid helium. I think I've heard of people getting to, maybe 900 millikelvin or something like that. But beyond that, it stops being a useful method to get to lower temperatures. Just because I have it, I'm going to show you the data. And so this is temperature and pressure. It's in maybe not great units. The pressure's in millimeters of mercury. So if you had a manometer, it's how big would your column of mercury be for whatever the pressure is. So an atmosphere is here. So this is 1 atmosphere. And so a column of mercury at 1 atmosphere is about 753 millimeters tall. And that's when your temperature is at 4.2 Kelvin. And then if you want to get to 1 Kelvin, then your column of mercury is only 0.12 millimeters. And so again, that's again reducing the pressure by 5,000 or whatever that factor is. Okay. When I was looking up all of this data for helium, I copied one more image, and I'm going to show it to you just to motivate what we'll be hopefully talking about later in this course. And so this is a plot. We didn't talk about this at all in this video, but I want to show you the data. This is a plot of the specific heat. So how much heat do you have to add to change the temperature of liquid helium as a function of temperature? And it's a really wild plot because what happens is initially when you're at 5 Kelvin, the specific heat comes down, it comes down, it comes down, it comes down, it comes down. And then right around 2 Kelvin, just above 2 Kelvin, it's 2.2 Kelvin. It has this weird anomaly where it spikes up and then comes down again. So this is actually called lambda curve. And it's because it looks, you know, a little bit like, looks like the Greek letter lambda a little bit. And so hopefully, well, not hopefully, we will talk about some of these funny effects that are seen in liquid helium as you cool its temperature. And notice that this is just 2.2 Kelvin is where this happens, and we can access this temperature range just by reducing the vapor pressure above the liquid helium. This is a quantum effect, and so we've gotten now into this regime where we've kind of developed enough techniques that we can get to low enough temperature that we can start to see quantum effects happening in our system of liquid helium. Okay, so thank you very much. That's where I will stop.